a block. It reads from left to right and from top to down. And this is what happened in a block. Uh, Note that this is the elements in a block, and this is the block in the matrix. So block is from left to right, and we also repeat it because we need more elements for the matrix multiplication. Okay, for example, if this is a 4 by 4 matrix, then the result is also 2 by 2. Then the result is also 2 by 2. But for one element, you need this and this, which is 2 times 2 for this and 2 for this. So actually, although it contains only 4 elements, you need 2 times 4 times 4. So it is more than the total elements.
The block is not safe in the achievement.
Block? Oh, block is it is saved in a string.
Is it in the string?
Yeah, it is in a string, so it's in the FIFO.
Yeah, but I mean, for the block multiplication, okay, now matrix is a block 2 by 4 and 2 by 2. For that, why is we need to 256 as what I mean is the block is not safe in the measurement.
Well, block, the local buffer.
It doesn't, yeah, it's not safe in the local.
It is safe. So, oh, yeah, so this is the naive case. Actually, this function access less than the naive case because we use block.
No, for the library function, okay, the form, the block is not safe in the measurement. That's my question. Why is there so many DDR That's very, it's not efficient.
Oh, the block is not safe in.
The subblock 2 by 4 and the subblock of the C matrix 4 by 2. This is two subblocks.
Uh-huh.
That you every time you do that you bring the element from the DDR.
Yes. Yeah, it is inefficient, so. Yeah, this is the read access from the global, from the DDR. Yeah.
I thought you should stick with the control memory.
Oh, because the size of the local buffer is only as large as a block. So if you after you read this one, store it in a block and write it out, then if you want to store this one, then it will be rewritten, overwritten. So you need to read again next time.
Yeah, so that
Yeah. That's the things that it needs to be improved. Yeah.
So, yeah, I think we need to invent the code, the block. Yeah, should be saved in the
Yes.
from the source code, we can tell, and this tell us read on
Yes,
from
because
the DDR.
yes, because local buffer it uses an array to store, but for the DDR it is the address. You will calculate the offset first and access the DDR. Yeah, so it's very easily to tell. Yeah. And this is the order of matrix B, and it reads from left to right and from top to down. Okay. And this is order of block. Oh, this the previous one is lemon, and this one is block also from out. And this one the block is from top to down and then left to right. And matrix X is relatively simple because we don't need for the multiplication, we just need for addition. So it's just left to right and down and top to down. And this is the order of block. And it only access the 64 times for x data of x, which is the number of the total elements of the matrix C. So we don't need to extra access the DDR like A and B does. Okay, so here's the function transform. Because as you know, the matrix multiplication is this times this, so we need to transform one of them to align each row and column. Also, with transpose, then it enables us to read only 256 times for DDR instead of naive case, which is 512. Okay, so the writing order of the element is like this. So you can see we just in this way and repeat again, and then we go to next row. So because we only read 256 data, so but the naive case, actually the total times we need the data is 512, so we need to double the time. So in this way, we can also reduce our access to the DDR memory. We store it in the local buffer here, and we write it out 2 times. So we use local buffer to reduce the time we access the memory. And this is the writing order of blocks in matrix A. And yeah, it is from here and then repeat it 4 times and move to the next row. And the order makes sense. You'll understand why it performs this in C times C equals A times B. And you'll understand why the order is aligned in this way. Okay, so this is the matrix buffer. And this is the function for the matrix B. So, okay, so yeah, we also need to double the number of data of the string to meet the requirements of the matrix multiplication. And as you know, the previous one is from left to right and then from top to down. So A is in this way, but B is this way and this way. So we transpose it. We make the order, which is the opposite of matrix A, so we can align the order of matrix A and B. And this is the order of the blocks. So it's this, and then repeat it again and move to this one. So 1, 2, 3, 4, and then move on to the next row. Okay, so now we can move on to the GNN block. This function is called GNN. So the block is this one first and times this one, so we can find the first half, only the first half of the GNN, because as you know, we double the time, so it is divided into the first half and the second half. And so this is for the first half. Oh, and for this block, the entire one should be this times this to derive the complete block of this one. But it is divided into 2 times, so we do the first time here. Okay, so once you read the output of the string from the matrix buffer, which is for matrix B, and also the transpose from matrix A, then you have the order like this. This is for A and this is for B. So this one times this one, you'll get the first half. Because the second half, you need the later part. And so, yeah, so in these 4 multiplication, you can derive the first half of 1, 2, and 3, and 4, which is the first block. of matrix C. And where is the second half? The second half is you need this one and this one to get the second half of this. Okay, so the next one, then you'll have also this time this will get this, which is the second half, and you repeat it to complete other three elements.
So for the first half, the media result is so in the local
Yes, yes, the local buffer is as large as a block. So you store it, and then once you get all the results, you just write it out. Yeah.
So for the matrix output, the resultant matrix, you only need to once. You do need to read from DDR.
No, we only need the DDR from the first function and the last function. From the first, yeah, only the first function. The last function is to write out. So this, we read it from the string. We don't read it from DDR.
All the intermediate results in the encrypted number.
Yes, it is in the string. So I move on.
Yeah.
Okay.
So, so from the whole operation, do you have an information that how much local buffer needed?
Oh, it is as large as the size of a block.
The size of a block.
Yeah, because this local buffer is reused by every block. You know, the block is
So you only need to save the size of a block.
yes, and it is reused by every block. Mm-hmm. Yeah. So this is also the reason that why the size of the matrix is not limited, because it is not dependent on the total size of your matrix, but it is dependent on your size of the block you define. So if you have a very large matrix, then you define a small block, then the trade-off is the latency. It will take so many cycles to compute to finish all the blocks. Mm-hmm. Okay. Oh, so this is the order of block of A times B, and it is from left to right and from top to down. Okay, and the input of G and C buffer is the first half and the second half, and here we'll add them up into the complete block. Okay, so as you know, we write them out two times. The first time is the first half of this, and then the 1 to 4 is the first half, and then 5 to 8 is the second half. So what we need to do is store them in a local buffer and wait for the second half. And once second half arrives, then we just add them up. And once we add them up, we write it to the output string from the local buffer. Okay, so this is the writing order of A times B, also from left to right and from top to down. Okay, so now we derive all the complete matrix C. Then we'll add it with X. So, that's why we read matrix X in the order of we mentioned in the GMM read ABX, because now the order is the same as the output of string of A times B. So we just simply add them up without need any local buffer. Okay, so the same. The order of a block is also left to right and top to down. And after we complete the GMM multiplication, we just write it out to DDR. This is the time we write it out to DDR, and this is which is the total size of the matrix C. Except you may divide by the DDR width, because you can write it out many elements in one axis. So the total element divided by the DDR width. Okay, so that's what we do with GMM write the DDR string. We transform the string to the DDR. And this is the element in the block. We write it from left to right and then from top to down. Okay, the block order also from left to right and top to down. Okay, so now we talk about II. The II is 1 because we can read DDR every cycle. You can see here we read DDR every cycle, so you can. But the bad news is the DRAM may have the latency because the burst is terrible. No, there's no burst because
the address, which is the array index, is not sequentially.
no, no. So no, it is not sequential. So only this one will have the burst, and for other one because you times so many things here. So of course the increment is not 1.
So for inner loop, say is
Say it's here. Yeah. Oh, so only these in a loop. This in a loop is burst. Yeah, but for this one is definitely not burst. Outer loop. This one, this one, this one, this one.
Oh, yeah.
Outer loop. Yeah. So the burst X is actually very terrible. So ideally it may be 1, but because you read the different page from DDR, so you need to wait for DDR to give you the data. So I don't think I would be 1 in practical case. Yeah.
So the inner loop is the first. Okay.
Yes. Only the inner loop is.
Okay. Then one question.
Yes.
For this kind of optimization, you always need to balance the memory throughput and computation throughput. If your computation. Okay. So when doing the design, you always want to balance the whole design. And in this part, let's distinguish the I/O bandwidth and the computational bandwidth. Okay. So since the computation is quite simple, right? Yeah, just a math. Okay, multiply and add. Okay, it doesn't consume too much resource. Okay, let's say that you if this FPGA run at 300 megahertz. Okay, and then you have a DSP. Okay, how many DSP in one FPGA chip? Thousands of DSP. Okay, and DSP, if 1,000, that if you can do 1K operation, okay, and then and running at 300 megahertz, that means that's how many? 300 and 1,000. That's 3 giga. Okay, 3 giga operation. Okay, and 3 giga operation, and if you are doing integer 32 bits, and you have A, B, C, and A, you have A and B. Okay, and that's 8 byte. Okay, and times 3 giga operation. So you have a 24 gigabyte memory bandwidth. You need 24 gigabyte memory throughput. Okay, so that's actually it's way exceed the current memory throughput you have. Okay, so in this case, if we fully utilize your PGA operation computation resource, then you will find out you do need provide enough memory bandwidth. Okay, and especially in this operation, that whenever you do a short burst, right, and then another access and take a latency, right, you will find out maybe you can only achieve the memory throughput, memory utilization maybe 50%.
Okay, so you will find out that to improve the performance, that you really need to figure out a way to improve your memory throughput. Okay, the bandwidth, memory bandwidth, or increase the utilization. At least you want full memory bandwidth available for you, and don't waste time to do the memory off-page latency. You know, if your access is random access and single burst, you will see the memory utilization will be very low. Okay, so you want to do two things. One thing you want to do long burst. Okay, the second thing you want to have a pipeline request. Okay, in this example, it doesn't have a pipeline. You have an inner loop. It's a burst, and then when it go out, then it's another request, right? So in this case, you figure out a way you want to increase the memory bandwidth, then you have a burst, try to increase the burst. And second, you want to do the pipeline. How do you do the pipeline? At least two requests can be piped. Yeah. So in this case, maybe you want to pre-calculate the address of a next access, which is not very difficult. That's the next index, right? You can pre-calculate that and then send another request out. Yeah. So that's just an example of that how to analyze the design. So maybe so for this really you want to get the insight, you really need to do the code simulation, the hardware emulation. Okay, and then look at the memory access. And then you'll get the insight. The memory utilization is really too low. It doesn't pipeline and doesn't do the long burst. Yeah, and then you come out techniques to doing long burst and doing the pipeline request. Yeah.
这样你可能要帮我解锁。
哦，没有啊。
Okay, thank you. Okay, so but once you read the string and in the string, the II is 1. So regardless of the DDR latency, then in the string the II is 1 because here you read it from A and you read it from B and you use pipeline. So yeah, for the multiplication, the II is 1. Also here you write C out. It is also pipeline. And here you write the X out. After you add X, you write out it also pipeline. So yes, in the operation, the II is 1. But it may be delayed because you don't have the data from DDR. Okay, so write. So you write to the DDR. Also, the offset is here, and only the last part is only this part is first, and for other part because here you write it in a block. This is a block, and this is the whole complete matrix, and you read this right in this way. So this is first, but this one not first. So you only have first here. So the II I don't think it will be one because you need extra latency when you switch to another burst. Okay, so here's the tool specific issues, and the makefile doesn't work, and we will have the error like this one. So I just debug and write the news just first. So for the code on the GitHub, you just need to execute the shell script, which is named ROM I wrote, and then you will complete the software emulation, hardware emulation, and hardware for you. Of course, if you just want to complete either one of them, then you just comment out the rest of the parts. Okay, so that's all for L2, and I'll give it to Zhongxian for L3.
Okay, good morning, everyone. In L2 API, the test bench generates the input and output string and the instruction code by a separated program, JamBean, but this is inefficient. So for the L3 API, we need to provide a software-friendly functions to be called. There are three forms of API are provided. We can either include a header file, C++ header file, or we load a dynamic link library. Also, we can import a Python module to use the Blast API in Python. So all the helper functions have the prefix *f+. This is the structure of Blast software API. For the kernel, there are interpreter to translate the operation code to distribute works to the different kernels. So for the GNN, we need to provide an instruction code to instruct the size of the two matrices and the total memory address of each matrix. So yes, the whole Flash library is loaded into FPGAs, and we utilize it with the Chinese runtime library. The XRT is packaged by a class Blast host, and it provides very efficient and simple functions to be called by API.cpp and Wrapper.hpp. The Wrapper.hpp is further included by typeflux.hpp, which is the main header file of the whole library. So if you want to write a C+ program, you can either include the source code of the entire typeflux host side programs, or you can link a precompiled shared library typeflux.so. Also, the shared library can be either linked by a C++ program, or you can use the load library function to load the entire library in the Python Wrapper class. The Python Wrapper class defines the protocol between the Python functions and the DLL library. So you can just import type plus L3 in your Python program. The main difference between the Wrapper.hpp and the API.cpp is that Wrapper.hpp, which is the source code of the entire host side program, you can see the return value is a status code, which is enum type, and there are additional checking to check if we initialize the internal class. The functionality is the same, but the return value is different. So we can tell that the API.cpp is more simple than the Wrapper.hpp. And also there are another function to execute the kernel asynchronously. In the Wrapper.hpp, we use the std feature. which is a standard library in C++. But in the precompiled shell library, we use OpenMP with some pragmas to realize the parallel execution on the host side.
So hold on here. So you may enter multiple kernels.
Yes.
And,
if your device has multiple kernels on it.
Okay, so for each kernel, you have
Yes. Yes. There are many functions provided by the webper.hpp, but most of them are eliminated in shell library because it merges the memory allocation and the set functions together to be type sent. It allocates the memory on the DDR and then it sends the data from host side to the device. And the get matrix is send the result from the DDR to host memory. And the difference between an alloc restrict and an alloc is that the restrict version of the functions in that the memory should be aligned by the row, and then some padding should be applied. But in non-restrict version, the memory may not be padded. The header file, the API will do the padding automatically for you. So the shared library version of the API only provides restrict version of the functions. Now, one two specific issues there is that when we want to compile the test bench, the host program returns this error message because in the C++89 and C++11, there are different name-mangling rules are used. The flag glib C++ use C++11 ABI is the instruction to tell the GCC compiler to use the new name-mangling rules. If this is set to 0, it will use C++89. So for example, the function with the argument in string, std string, will be mangled in the C++03, it will be mangled with std string, but the C++11, it expands the sender string to its inherent. Another function for the getCU names, the C++11 API appends additional information in the names, in the mangled names, so it can be linked. It cannot be linked because the mangled name is different between the XRT library and the mangled function. So for the test spec, this is L3 testing phase. The host program generates two 128 matrices with 14-point entries, which means it will do the 14-point multiplication and addition in the kernel. And it generates the input and then verifies the output in the host program. This is a function usage of the function code. And in the beginning, we will to create a handle for the kernel by providing the tcl bin file path and some configuration files and the number of kernels. when the handle is created, we allocate the memory on the host side for the matrix A, and then we also allocate the corresponding memory on the device. And then after allocating, we send the data from the host to the device. If the operation is failed, we destroy the handle, which is generated before. So before we end the program, the handle should be destroyed to release the kernel.
So before the FPGA kernel function can start, you need to move the whole matrix to the FPGA side.
Yes.
But matrix multiplication is a very typical operation for a lot of applications, and especially those applications have very big matrix, like a big rating. That's the nodes maybe thousands, more than thousands, maybe millions of nodes. And you want to move the whole matrix to the FPGA side.
Okay. After sending the entire data to the entire matrix to the kernel, we can start our operation with type plus GNM, which means we will send the instruction to enable GNM by passing these values, which is the height and the width of the two matrices A and B with the kernel numbers. After the execution, we get the result back and then free the allocated memory. So thank you for listening.
So for this, unfortunately, I didn't see the performance analysis, especially the memory. So it's good that you start with the latency and analysis, so that you have a whole picture on the whole data flow. And then once you have an idea about the internal operation flow efficiency, then look at the memory access.
We did calculate the total number of memory access in the previous slide.
So for the memory access, that here is how many times the memory size.
Oh, here is the number of memory access.
And we'll translate to how many metric size data.
Oh, it depends on your process out of C and times this one. Yeah. This time, then it will be the total memory access, because this is the number of blocks in matrix C and this is the number of elements in a block. So only this one.
Yeah. Give me an actual number. Yeah.
It depends on your parameter. Here is for 8 times 8 times 8.
So parameter, what's the parameter that affect the memory? That's block size.
Yeah, it depends your block size, and because for this one, it means the block number of blocks in a row. So
just take this example. You have A matrix 8 by 8, B matrix 2 by 8, some matrix 8 2 by 4, B matrix 4 by 2. In this example, how many of 8 by 8 matrix need to be?
8 by a matrix, and it will be 8 Yeah, 2 over A. Because, oh, A by A by A. And which size is your block?
For MSC, this is the for MSC subtraction 2 by 4.
Yeah, 2 by 4.
B is 2 by 4.
Oh, then it will be 8 over 2. Yeah. So that's what we got for here. Yeah. 8 over 2.
So we need to read the whole time.
Yeah, 4 times. So that's why it's 256 because it is 64, which is the total matrix size times 4.
So we need to read the matrix whole time.
Yeah, if it, in this case, because you can define other matrix size and also block size.
And even on the block size.
Yeah, also depends on your block size.
The
So,
block size decide how much your local storage.
yeah, so the smaller the block size is, then you have a smaller local buffer, but you need to read the BDR more. Okay. Well, today we will give a brief overview of Whitey's Vision Library. Okay. So, in today's presentation, we will only give some very preliminary observation, and we indeed spend time survey these things. But I think after we set up our own device, we will intensively try more things. Okay, so about Whitey's Vision Library, we can see its library function here and several examples. Basically, every function you have in the OpenCV is a computer vision library. Basically, almost every function in OpenCV you can find a counterpart in the Whitey's Vision library in the namespace XF and CV. That is, we have a hardware accelerated version OpenCV. And OpenCV is often used in NN training frameworks such as Darknet, which is written in C and C++. Okay. Also, the reason we survey the Whitey's Vision library is that we want to develop NN applications. And recently, we noticed that, for example, there is a conference called Design Automation Conference. They hold a competition about deploy NN to FPGA, and this competition continues several years. So I think it is good to survey good methodology to do this kind of things. And our goal, our preliminary goal to use Whitey's Vision Library is to implement a function augmenting training image, because during the training, you want to increase the model robustness, and therefore you can reduce overfitting. So although you have the same training set image, but in each iteration, in each epoch, you slightly change the training image. For example, you can flip or adjust the color saturation.
in the past, in a typical NN training flow, this kind of thing often done by, for example, GPU. And sometimes if you don't have GPU, you use CPU, then your performance will be maybe at least 10 times slower. So here, FPGA provides us an extra option to do image processing, so that potentially improve the training process. So in this in our experiment, we have three components. First, because we want to reuse existing framework, so we see from L1, L2 to L3. We see in each example which one gives the best template. We found that there's a good function we will introduce later in this example called blob from image. And we also did something here. We migrate some function from library 2021 to 2020.2. The reason we do not directly use 2021 is that we prefer a conservative develop flow, because in different toolchain version, it is often it is quite possible that if we directly use a newer library, then our toolchain might not support that. So we decide to use the library, those those headers consistent with our Xilinx toolchain on the core server. So we start from 2020.2 version, and when we need some extra thing, we analyze the structure dependency and incrementally migrate the thing we need to reduce the time we need to debug. So this is the second bullet. And oh yeah, because we have something unique in the Xilinx Vision library, the Bytes Vision library, so we need to implement corresponding host program in the test bench. So these three things consist of our experiment shown here. Basically, we could have some simple utilities, for example, resize, crop, flip. These things, all we can find OpenCV, or we can find this function in OpenCV and their counterpart in the Bytes Vision library. And all the functions in the Bytes Vision library, they share a similar template. For example, the template is in this form. They often share some common template argument, and we summarize the most frequently appear template argument here. For example, we might need to specify the output PTR width, that is the unit width of output AP type data, and also output type. Output type means, for example, this is a typical pixel size. We have 3 channels. Each channel is 8-bit, and U is unsigned. And we also need to specify max height and max width of the image. And later in the functional argument, you can send different image size to the accelerator or FPGA. But before that, when you synthesize a when you synthesize your kernel, you need to specify the max size, the max dimension of your image for the hardware synthesis. The last is NPC, means the number of pixels processed per cycle. This means, for example, when you process the image in the kernel between the module, you probably send the data by string, and if you change this template, for example, number of pixel processed per cycle here is 1. If you change it to 2, 4, or 8, then you can perform something like in string, you string pixel 1 by 1, but if you increase the NPC number, you can send the pixel in a string more. And for example, you can send 2 pixel, 4 pixel, 8 pixel in the streaming one time. There is some good function we found very useful in the blob from image example in the level 3. And this function is called Preprocessing, and basically, wait me a second. Okay, basically the function, there is a function called preprocessing, and the function is like this. And in summary, although this function can do a lot of things in one shot, but we can control what the function do to the image by operating code specified here. We take optical 0, for example. Optical 0 means we do mean subtraction. What is mean subtraction? Means the result of mean subtraction is something look like in this image. Yosan, maybe you can, I remember you wrote the test bench, maybe you can give some comment about mean subtraction.
So in image preprocess, we may want to normally we say we want to normalize the image. So I think it is a special case of image normalization. So so here this is the image normalization. We will minus the subtract the mean and times the standard deviation. So it's some kind of image preprocess we like to perform. Yeah. So.
Okay. Because I forgot what is the means of subtraction. Thank you. Thank you for your son's comment. Yeah. So we can besides this, we can by specify different OP code, we can do different things in one shot, as shown in here. We did some preliminary observation. For example, from the synthesis text report, we can see the estimated clock period and latency, mean latency and max latency. And we can also read from the text report about the resource usage about VRAM, DSP, FF, and LUT. And we can observe the software latency and hardware latency. That is, we run, I think software is software emulation, right? Uh, oh, no, the runtime of OpenCV. So it's run on the server host side, the CPU.
Oh, okay.
Software, yeah, software. And hardware is that the core server use the acceleration card. I remember not pink, not pink, U50. Oh, yeah, okay. So we can see 26 times speed up by using FPGA accelerator. But we just set up our own GPU, and later we will set up our own FPGA, so we can try more things. And later we will share, compare the how much accelerate, how much speed up that FPGA compare against a typical GPU. Yeah, we run pre-processing and resize and flip. Oh, crop, also crop. And we compare something and would like to discuss with you guys. For example, we compare with or without string. The only difference is the synthesized report. We can compare the text report by the diff comment. And surprisingly, the synthesized report with or without string, the difference is only 9 flip-flops usage. And other metrics are the same, including delay. And the other thing we don't understand for now is with or without data flow. If we turn off data flow, then the kernel seems it stopped mysteriously. And currently we don't know why. It just hold there. Yeah, we deactivate. We comment out the data flow pragma. It holds. Yes. Yes. We will continue survey analysis and try to analyze the reason. Maybe sometime at some point in the future, we will find the answer. Okay. So suggestion for improvement. Maybe we can, because we see in the participation library, some of the functions do not support the string. Although in C++ we have polymorphism, and we can, those function library, some of them support string natively, but some of them do not support string. So the option 1 of improvement is that we implement our own version, and such that those functions can support string. The other option is we can do some host level parallelism. That is, we can instantiate, that is, we can create several instances of the kernel, and we can run multi-threading. Each thread will monitor a kernel, such that each thread will keep the kernel, its own kernel, busy. Once the kernel complete its job, we send a new image to the kernel and receive it back once the processing is complete. So this is option 2. Okay, we provide some extra supplements. For example, thank you 助教家福help us to resolve some compatibility issue that is in the Xilinx tool. In V plus its compiler is V++ 2020.2. It does not provide up-to-date std C++ library. We found that we can directly replace newer std library to the Xilinx pace, and everything worked just fine. So we are lucky and glad. And another thing is that so far we incrementally replace some newer Vitis vision library infrastructure, those data structure back to the 2020.2 version of the Vision library, and so far it works well. Yeah, this is our observation. Thank you.
So you mentioned that some of the one function doesn't have the stream interface.
Yeah. For example, flip.
So when you want to develop a data path of a new vision function, you write each function that has the stream interface so that you can put them together easily.
Yeah.
So that's good. So now all the kernel functions has the stream interface of Optical to compose.
Okay, thank you.
Okay, hello everyone. We are Team 4, and today we are gonna introduce the Vision library, and what we are going to focus is one of the L2 or actually it is L2 level kernel function. It is called warping, and actually itself can be as part of the L3 level API. And what we are going to do is to develop host code in OpenCV, and we are going to build an application for warping. And also, we're going to do some benchmark about the warping function. So it does not itself contain too much L1 kernels. Later we'll see it only contains 3 L1 kernels, such as array to metric to array, and then the core part is the warping itself. And why we are going to introduce this API, because we might use it in the final project, and also here we are going to show that how we are going to develop a host program in Vitis and accelerate the part we want to speed up. Okay. Okay. In the beginning, I will introduce what is warping. And so, suppose we have two images, and one is called source, and another is called destination. And what the warping do is, we want to calculate the new x and y from the source image to the destination image. Yes, and there are two kinds of warping, and one is called forward warping, and another is called backward warping. And when we finish when we get the new x and y, and we can do the, and we will give the how to say the, and twice the pixel value, and in forward warping, and if the pixel value is same as the source image, but in the backward warping, and we calculate the x and y by, we will how to say, we calculate the value by the interpolation. Yes. Yeah. And how to get we need a transformation matrix, because this is our formula, and this is new x and y, and this is the old x and y. So we need a transformation matrix to calculate the relation between these two images. Yeah, so this relation is called homography, and homography is 8 degree of freedom. So if we need to get this matrix, we need have 4 corresponding point between these two images. Yeah, and if we we have 4 corresponding point between these two images, and we can use this formula to calculate the homography. Yes, and once we get the homography matrix, we can easily calculate all x and y we can easily get the new x and y. Yes. Okay. Let's move on to the kernel code.
You want to find the matrix.
Yeah, in the beginning we need to find the matrix, and once we get the matrix, we can get the relation between these two images. Yes.
Okay, so this is the hierarchy of the function in this code, and this function is right in L2, and this function will be defined in L1. And there are 3 functions in the warp transform acceleration. First one is we transfer the array into the XF matrix, and then we do warp transform on it, and then we transform it back. In this function, we write the input matrix into this function by input string and write it to the memory by output string. And then in this function, there is a two-level netlist loop to write the input image in the buffer, and then we calculate the position. We need to take the value we want it, and then we go to this buffer to retrieve that value and then write it out to the memory. Okay. And so this is the 没有吗？有。This is some special data type defined in this code. The first one is the first one is pixel type, and there are many of it, and we only list two of them here. The first one is if the image is in grayscale, then the pixel type will be this, and this means that there are 8 bits per pixel and only one channel. And if the image is an RGB image, then there are 3 channels. So the pixel type will be like this. And then the second one is pixel level parallelism, which is mentioned in by the previous group. So this data type means how many pixels the kernel process per clock cycle. So there are different options here, and so if we use this, then it will process 4 pixels per clock cycle. And this code is defined in the types.hpp. And it will define the pixel type and the pixel level parallelism here. So it will store many different things in this data type. And we use this in stream and to store, we use this data type in stream and buffer, which we store the image pixel. Okay, so this section is about Iostream. As I mentioned, that we used a data flow in this function, and so here is the input string and output string, and we can read the input string in parallel, which we use this function to control the pixel level parallelism. And this is what we mentioned here. Yes, so if we use, for example, MPPC2, then it will read 2 pixels per cycle in this string. And Oh, okay. Also, this input string is defined here, and output string is defined like this. And this data type is retrieved from this data type. Okay. And here we talk about the buffer. Okay. We used 4 memory blocks in here, and since that we do back for wrapping, we need to do bilinear interpolation. So we need if the position of the output image is not integer, then we need to find for example here, and we need to get this 4 value. Then we calculate which one we need to take that value. So we assign each pixel to one memory according to the parity of its column and row. So for this is in even column, and this is odd column, and this is even row, this is an in odd row. So we put the same parity in the same buffer, in the same memory blocks. So if we need to get these 4 value, we only need to take the same column of these 4 memory blocks. Okay. And the memory size here is, the memory size here is store rows times image width. And in the code, this is 100. And this is, okay. And then since we need to partition this buffer into 4 memory, so the one block size is this. We need to divide it by 4. Okay, and we write 1 pixel per cycle. And if the buffer is full, for example, this is the buffer. So after we write this block, this is the image. After we write this block, then after we write this block, then if we want to read this block, then we need to override the origin value in the buffer. And if the pixel we need to take is not in the buffer, we write 0 to the output string instead. Here is what we're doing in the main loop. There is a 2-level netlist loop here, and the loop bound is like this. We can see that the upper bound of the outer loop is the total row of the image plus the start row, which is 50 here. And this is because we need to go to buffer to take the value. If we don't read this 50 rows. 50 rows at first, then we might 要怎么讲？好，讲中文好了。我们可能会找不到里面的值，就是如果我们不先读那50个 row 的话，我们可能要回去找那个位置的时候，那个值还没有被读进 buffer， 那我们就会找不到它，我们就会把0写出去，这样就会全部都写0出去，这样。对，所以要先找50，先把50个 row 读进来。那因为一个 buffer 的大小大概是100，所以这有点像就是那个乒乓 buffer 这样，就是它会先读50个进来，然后这样对，学长讲的，我都是这样子。
Because what homography does, we cannot estimate what accurate the next pixel will be completed. So this is kind of random access. So we have to estimate how many rows the pixels should be read first, and we have to estimate that.
So the 50 is your estimation.
So if it is not that much, we might encounter some scenario like if we calculate the value but it is not stored in a buffer, then we have to output 0. So it is the output might not be correct. Yeah. And also this will affect the buffer size. If the homography motion is very large, and we have to store more than 50 rows, and the ping pong buffer will be more than 100. Okay, just a little comment.
Okay, so the steps in this main loop is first we store the input image in the buffer, and then we compute which pixel of the input image should be outputted after 50 rows. And then we do bilinear interpolation, then retrieve that pixel from the buffer, and then write to output. Okay. Okay, and here's the section of kernel optimization. Although there exists simply like parallelism, but the loop bound of the main loop is fixed to the UHD, which is 4K here. And seems that the parallelism just 好，我讲中文好了，就是就是它虽然外面都有做平行化，但是它的 main loop 里面，它 main loop 这个最肥的这个地方，它里面是没有做 unroll， 还有就是它里面是没有平行的，虽然它外面在，对，但它里面都没有平行，所以就算我们外面就是这个是16倍平行，然后这个是4倍平行，但是它还是有一个很大的 bottleneck 在这边，所以它的 latency 其实也没有办法用那个 NPC 压下来这样。
So that's a data flow, right?
Yes.
Data flow. So in the middle of the stage, that so the rate in the middle of the stage is now optimized. Yeah. So the output will be limited by the function.
Yes.
We think that this is one of the optimizations we might have a chance to optimize. Yeah, so we can see that this. Yeah, we can see that for this for loop, the latency is this number, and actually it is this number divided by 16, and 16 is the parallelism we set. So actually we can read the pixels in parallel. However, when we feed it to the main loop here, it actually it cannot be parallel.
This one, the latency and the interval is the same.
Yeah,
Yeah.
yeah, and
So this one doesn't do the pipeline.
yeah, and another thing is that uh, because the loop is written with a fixed number of a bound, so if we want to modify the code, I'm not sure how to really to change it into a way that we don't need to really modify very much. I mean that, yeah,
It is in the bit distribution that
yeah,
provided by that.
yeah,
So since this kind of code is now
flexible. Yeah,
for library function.
yeah, it's not flexible. So, for example, if it is written in the thin HLS library, it will not written like this way, and the loop bound will be adjust to what the parameter you set. Yeah. And
So you have plan to improve this library and submit.
we maybe. Okay. Yeah, and we also put it to the U50 system, and we evaluate the gray image configuration, and the CPU here is run in the VTIS environment, and we use the CPU in the workstation, and we use the Kernel from STD library to measure the times. And we can see that if we consider only the kernel time of the FPGA, it actually can achieve real-time performance for 4K gray images. And however, we have to account for the data transfer. However, after considering the data transfer latency, it it at least had 10 times better than the CPU version. And hey, yeah, if we perform actually, this is a single shot. We just measure one image, and what we previously wanted to do is to give the host program a video stream input and try to read the data, cover the data transfer into the kernel execution. However, the OpenCV video string part, and we have some problems when compiling with VT's environment. Yeah, so now we just only give a single short version here. And what we are trying to do is something like this. It is a 4K input image, and here we first detect the marker corners in host side, so not the FPGA. And after the corner is estimated, the homography is also computed in the host side. And maybe we can move this into the FPGA side in final project. So actually what in this work did is the inverse swap. So we determine each pixel in the destination image here, and we're gonna ask what is the source pixel after applying the inverse homography transform, and we pick the correct value. Actually, our source image is from the template here.
The homography estimation is the calculation to the metric.
Homography, yeah, estimation is the calculation of the metric itself. And after, in this lab, we assume that we have already gotten the metric, and because the image size is very large, it's 4K, so we only accelerate the inverse swapping part. Per pixel metric multiplication problem. Okay, and here we want to introduce actually many people might just run the makefile, and it's good because makefile, if you use makefile, you don't need to really click the GUI mode. And however, because for the final project, we might need to include some additional host program libraries that cannot be synthesized. So actually, in this lab, we run this program in GUI, and what we want to introduce is actually it is very similar to Visual Studio if people working on Windows system, and because VT's library suggests that we use the OpenCV version of 4.4, and I'm not sure if it is on the server, so we compile OpenCV from source, and actually compiling OpenCV 4.4 needs a newer version of CMake, so we also compile a new CMake version to our local home directory, and we simply add include file library path and the symbols of these included host code library. And what you really needed to do is, for example, for your kernel code, you just right click the project here, and here select the properties, and then in the settings include, you can set the include path. For example, we need to include the L1 kernels in the vision library, such as the data types or some very deep level include files here. Also, for the host code program, you need to modify the properties here. You need to include, for example, the OpenCV library symbols in the library path itself. And this Xilinx OpenCL is for the XCL header file. So actually, it is the same as what people write in the make file, but we just show everyone that it is tedious if you use GUI, but it is actually just doing the same thing. Okay, so after this thing is settled, you can use the VTIS IDE to compile just like Lab 3, and then you can write the image or read the video string from OpenCV successfully in this IDE. And for the summary part, actually, the host program is written by us. So the time measurement and the matter detection and homography estimation is written by us. So what we actually accelerated is the warping part. So this is the flow that bring us to give an application and marker homography estimation application and accelerated in VTIS system. Another thing is that the memory array is, in this case, we use 4 memory arrays because for this algorithm, we are using the interpolation of the bilinear interpolation here. So we need to, the memory structure here, we need to design for a given certain algorithm. And another thing that we show the library import as well as the host code can all be run successfully in the GUI mode, just like in Visual Studio. And some things we would like to do is to add video stream. So there might be some things need to modify in the host program. For instance, after programming the bit string, we have to write the memory to we have to write the input image to the global memory. And actually the image is changing every new frame. And we have to cover it, we have to we have to perform it in parallel. So in the host code, we have to read the image and execute the kernel in the command queue in parallel. So in order to cover the data transfer.
And you will have three process. One process continue feeding the video stream, the kernel function.
Yeah.
And
right.
another process reading from the output.
Yeah. Yeah.
And okay.
Yeah.
And so for the kernel function, these three concepts on the FPGA part. Right now you are talking about the host function interact with the kernel function.
Yeah.
Okay, and you want to do the real-time streaming.
Yeah.
The frame continuously.
Yeah.
And right now the kernel function you have to trigger the kernel function. Right?
Yeah.
Yeah. So maybe you probably need some kind of a host to kernel function streaming, so that you eliminate the synchronization between the host to kernel frame by frame. Right now, the frame you have to initialize the kernel.
Yeah.
And trigger it.
Yeah.
Yeah. Right now, in this case, you should use the frame data to trigger the kernel function.
Right.
Yeah. So that means that's another architecture. Traditionally, you learn
Okay, so far you learn the host function and the kernel function interface by very simple XI Lite interface. Okay, you program the argument and then you say AP start. Okay, but for this example, actually you have a friend streaming in. Okay, and this synchronization between host and kernel function gonna take a lot of overhead. Yeah, so the best way to do it is the host to kernel using stream. Yeah, right now all you learn the streaming is between the function of a kernel function, you do the stream, right? Right now you have to think the host function is part of the data flow workflow. Okay, then the host actually feed in each stream. You actually send the frame start. For example, there is a frame start message or a control stream. Okay, and then the host function simply write to that stream. Okay, and followed by the frame buffer in the system memory. Yeah, and the kernel function, you have a process reading the frame, sitting, waiting for the control message, which is a stream. Yeah, once you listen, you hear there's a stream, control stream message in, then you start reading the frame buffer. Yeah. So, and the frame buffer got to be arranged in like a ring buffer. Okay, so for the image capture the image in, then you put into a ring buffer on the system memory. And for the whole for the kernel function, once you receive the control message, and start reading the frame in a ring buffer. Yeah. So for the system design, you just need to be careful design. It doesn't have an overrun or underrun. So that will in turn decide how many entry of the ring buffer you're gonna provide to buffer the, because the system, when system running, host function may have other process running, right? So host and the kernel pretty much run at a fixed speed, but the host function can to be varied because there are other processes on the host. So it can be faster or slower. So you need a buffers. Yeah, there. So we are assuming host is running faster than the kernel. Okay, however, the host sometimes may be slow. So you have the ring buffer to buffer the variation of the host latency. It's very conceptual, but it's interesting to explore this communication scheme. Yeah.
So that is the end of our presentation. Thank you.
Like, for example, the frame size, frame image size, that kind of things you only do once. But you don't need to do frame by frame. You still need the XI line. It's only for the very early initialization. And once it starts running, that for each frame you don't need to do当 data 是 yeah， 但是我们今天讲是每一个 frame 要开始做事情，可能方可能每次要碰，对不对？要一个 kernel 方处理一个 frame， 所以每一个 frame 你要有这些 control 的进来。The problem is we want to eliminate. So let the data 但是在光分析也要另外一个写法，那个不需要每次，因为欧分析你还是要叫那个欧分析的方程不需的发火嘛，对，然后要透过那argument，然后叫它开始去这个 task， 对不对？对，还要做这些事情。那这些就是我刚刚说的，因为每一个那个就变成一个灾难，你叫他去做事情，现在那个都不要做，都不要做。那所以你在比赛那个kernel function的时候，你就要有一个 process， 就是所谓 process 就是有一个 hour， 一直在 listen 那个 stream， 那个有没有 empty， 有 empty 就开始收它的一个 control stream， 对，那你收到然后就你就给那个 control stream， OK， 然后你就录的去做分发。大概这样。
Okay. Hello everyone. We are Group 1 and today we're talking about Lab C corner tracking with optical flow. Okay, this is our outline. Okay, first we talk about what is an optical flow. Optical flow is a pattern of apparent motion of object or edge in a visual scene caused by the relative motion between, let's say, the previous frame and current frame. And the optical flow can be used by, let's say, robotic or some image processing, etc. And here is the example of the optical flow. Okay, then how do we estimate the optical flow? For example, here we have a location for a 2D image. So we will have let's say a point x, y at time step t. So let's say it's xyt. With the intensity xyt means you can think it is a pixel value. And we can say, for example, next frame, the same pixel may be moved by the delta x, delta y, and of course delta t because it's next frame. Then we can say the intensity of that pixel, the same pixel, so the intensity will be equal. But the location and the time step will be different. So we can have the equation 1 here. And assume the motion is very small. So we can use the Tyler expansion to make this term into this term with the higher order term. But since the motion is very small, the higher order term can be truncated into 0, for example here. And then we subtract this term because the motion is very small, so we can say it's close to 0 here. And then we divide it by the t, which should be constant in the video frame, and we can derive this function. And since we have this function equal to 0, then we can solve this equation, then get the motion of the pixel. So this part will be EL. Okay. Okay, so for this application, just because we
use an example from the BT's library, and it provides the example is how to use article flow to improve the corner tracking. So here's the architecture, because we want to corner tracking with the Harris corner detector. But for the right part here, so here is the current frame. So here is the current frame. And here is the next frame. So for the current frame, we will use the Harris corner detection algorithm to detect a corner to a lead. And we will use the article flow from current frame and next frame to get the article flow. And then we will use the article flow to update the corner to get a better corner estimation. So here's the Okay. So for the left part, left side, there is a host function. So the pseudocode is simple. Is we read each frame from the video, and then we will use a for loop for each frame. And first we will compute the corner, and then we will compute the article flow. Corner, article flow, and then we will update the corner. And so for these three functions, we will use the HLS kernel to accelerate. And for the right part, this is a corner tracking accelerator. So this is a function of corner track. And it was used, it's just a function called Harris image. And the Harris image implementation is like this. We will use, first we will convert the data into the OpenCL in the kernel, in a vision L1 function array, and then we will use a corner Harris function, and then we will convert the corner to a list. So for these three, this is the L1 function in vision library.
So on the left side, the host function.
Yes.
The function is the L2 function.
Actually, in Vision library, there is no L2 function and no L3 function. It only has L1 function. And the L2 function and L3 function is the combination of L1 function.
Combining the L1 function. The question is, in the host function, how does it know the first function will complete? If that's a kernel function,
yes.
remember when you write the OpenCL code, you actually have to fill in all the arguments and then wait for it.
Yes.
Okay. And so for those operations, wait for is complete, for example. So it's inside the host function. Right?
Yes.
That the component
Okay, so I think
that's one question. The second question is, yeah, actually, in the host function, we call this kernel function.
Yes.
Right. And so for there are data exchange between those kernel functions. So the data exchange is through the host memory buffer, host memory.
Yes, they use a OpenCL buffer.
Immediate result, you have to move the host memory.
Yeah, I'm not sure it's host memory because it's create the OpenCL buffer. And they use a buffer.
So it's possible the data exchange through the global memory on the FPGA side.
Yes, maybe. Yeah, it's possible.
So the next question is it possible for these functions you actually using the streaming?
I think it's possible. Yes, but it's only for the corner update accelerate.
Not bad with the flow, for this one. Okay. So actually, you have actually in this part you have a three kernel function. That's one kernel function. Right?
Yes.
That part is one, right?
Yes.
This is another one.
Yes.
Okay. So if you want to make these three kernel functions to interface them by string in the FPGA without using the host function to do the synchronization. So you may think of how look at that. It's not simple data flow. Not simple whole data flow.
Yeah.
Yeah, but it's possible. Yeah.
It's possible. Yeah, possible make here. We can make string here, but for these two, yeah. Yes. So for the two friends, it can only be done parallel.
Friend by friend, many friends.
Yes. Yes. Yes.
Think about it.
How
to make those three kernel functions.
Make in one kernel function.
In one kernel and interconnect them with the string. Okay, and consider this computation topology and refer multiple threads.
Okay.
That will be very
Yes. Yes. Oh, okay. So this corner. Okay. So this three is L1, and maybe we can call this is L3. Maybe. Yes. But because the library didn't write this function into a API. It just write it into a function file. Okay. So as the same as the corner tracking, this you can think this L3 function here, and the L3 function use these 5 L1 function, and this is optical flow. And for the corner update, you can see this is a L3 function, and it only use one L1 function here. So for the L1 kernel function, the most of important one is for this. Yes, it's for this 4. And Yanfu will give an introduction of this kernel function, how it's implemented. Yeah, it's okay.
Okay, then I will analyze the kernel function code here and also show some pragma we used to introduce in our lecture. Okay, the first one, the NPC, the previous team, I think we have the same discussion, so I will skip that part. This part is how can we turn the array into the XFMAT, and then what is an XFMAT? It is used in the Vitis library for the image data type. So first we have to transfer the entire data pixel by pixel into a XFMAT. So you can see here, for example, with the one read, let's say data in, and we will transfer from AXI to mat in this entire function using data flow here. And the stride is just, if you set the stride into -1, then no stride. Okay. And the next kernel function is corner Harris. And here, first, you can see we use also data flow pragma here.
and some FIFO depth equals 2. And the entire flow will be this. First, we will perform a Sobel filter, and then we can get gradient x direction and gradient y direction matrix. And we will duplicate both gradient x and gradient y mat here into this two. And we will perform first square to each pixel in that matrix. For example, here is we input the x1 and y1 and get the square matrix. And then we take the x2 and y2 to do the multiply into gradient x multiply y. Then we will get, for example, these three matrices here. And then we will perform a box filter. It's simply just a smooth filter. And then we can compute the score. Let's say if we have the matrix here, the matrix x square and y square and xy, and we'll get this matrix M. And then we can calculate this, let's say, Harris response with this formula. It's basically the determinant of the matrix M, and K is a constant range from 0.4 to 0.6, and with this. So, okay, back to here. And one thing notice here is first in this pragma we can see, okay, we do the array partition on the source buffer 1. And how can we do this? And since we first read the entire matrix into a buffer, and then we use this buffer to perform the operation we want. Okay, and here is the same thing. Here is calculate this Harris response. And one thing we can notice is we use the DSP with latency equals 2 to the both response. Okay? And after we calculate the response, we need to compute the score. And basically, it's the same. Okay. And after we compute the entire response, and we can get a matrix of the score. And for example, if we have an image here, and there is a square, and maybe we will get 2 corners detected here at the same edge, and we don't want that. We want only one corner at one corner in real case. So we will perform a radius equal to find the local maximum, and then we can get a corner with like this to reduce the noise, for example. And then we get those 4 corners, then we add it to the list. So now we will have a list with corner. And in each list, we will have the location. Okay. Then next, we have to compute the optical flow. No, because you have the location here. So all you have to do is once you have the pixel motion, then you find the location and query the motion back to the corner. Yes. Okay. Next, then since we already have the corner list, then all we have to do is compute the optical flow. Then how can we compute the optical flow? First, we will have to perform a Gaussian filter to extract the feature with Gaussian pyramid. So here is the example kernel used in our code. And here you can see here is how we compute the dense optical flow. First, you can see here we use string, which is 5-fold, and the depth is 64. And the interesting part is it's a hyperparameter because you don't really sure what to set, so you have to perform some experiment on this parameter. So in this case, they use 64. And then we will have to 5-fold, for example. And first, yeah. And first, we will have two vector u and v, and it might be downsample previously. So we might have to perform scale up. For example, originally is n, and this might n minus 2 up to n, back to the original dimension here. And another thing is we can use a coding cell like this. If we have URAM here, then we can do those pragma, and maybe we use block RAM, for example, then we can do the rest the same in this coding style. Then we need to find the gradient of the u and v vector. After we find the gradient, then we can solve the Hessian matrix. The detailed computation will be written in the report, so we didn't demonstrate here. And after we find the Hessian matrix, then we can solve the equation, and then we can get the flow. After we get the optical flow, we will perform a medium blur filter to smooth out the noise. And then we will get a two result, which one is U and V, the optical flow. And then we will stitch into single data string and string out to the next stage, which is update the corner. Okay, and here is what I said is when you are in this Hessian matrix, you will need the intensity first. You will need intensity and square and multiply. And so you can solve this in iteration algorithm shows here. You will solve this entire function until it converges on the host program. Yeah, those function is on the kernel, and the iteration until converge is on the host. Yeah. Yes.
You dig into how they communicate to the synchronization.
Okay. And then it's the performance analyze.
Okay. And first is the corner tracker.
And we can see the timeline. First, we will create a buffer, and then it is similar to the lab 3 we did. So and in the code is the flow is like this. And we can see in the timeline it is the same. It is the same the code. So okay. Oh.
Conclusion.
Continue.
Okay, then.
Okay, and this is the result we get. And first, we use the pyramid down and to build the 5 size image, and we compute the optical flow and to find the kernel.
So this is run on the U50.
Yes. Yes. And this is the kernel we find in this image. Yes. And okay.
So did you do the analysis on especially the iteration on the whole size among those kernel functions?
Yeah, I think that's the application timeline we skip there. Yeah, go like this.
Oh, yeah. So that's the iteration part, right? The whole application timeline. Oh, okay. So there's one iteration, another iteration.
And this is the for image, and the iteration will do in this. The optical flow will iteration in yes.
Okay. Yeah. So yeah, in your time, you think about how to make the whole workflow all into the FPGA. And that's also a little bit complicated application topology. And also multiple frames, and all the module frames include both sides. Okay.